So this is the last problem in the first problem set for ECE/ME360. This was, I think, easily the most difficult problem of the problem set. And yet, if you take your time and look at the equations as that you develop them, remember what your endpoint is. What are you trying to do? You'll see it's pretty straightforward. And as I walk through the solution, I know that I make it look easy, because because I have a lot of experience in this. But even I will sometimes kind of go down a rabbit hole and go down and find myself in a dead end and have a bunch of mistakes and throw out the solution and start over. It is the nature of these problems that they take time. You get better at it because you get more careful with your algebra, so you don't make those mistakes, and you go down fewer rabbit holes. But there's really no magic formula here. It's just you just have to try things out. So we have a two-loop circuit with two resistors, an inductor, and a capacitor. We have an input voltage applied, and we have values for the four components: R1, R2, L, and C. And there's four parts to this problem. The first is write a differential equation that relates the voltage across the capacitor to the applied voltage. Okay. The second one is to write another differential equation in terms of I sub L. So these are what we now know are input-output models of the system. Both of them have E sub I as the input. One of them has the voltage across the capacitor as the output. The other one has the current as the output. And we know there'll be similarities between those. Those differential equations will be very similar. Part C is write those characteristic equations, and what you'll find is they're the same for those two. And then the last one is a bit of a stretch, but I want you to be thinking about this, is given those values, what can we say about the response of the system? Okay, and so that's something we'll walk through. So let's go to the solution here. Here I redrew the system and showed E sub O here. You could have called it E sub C if you wanted to, or anything else, but that's the voltage across the capacitor. We know that's a variable that we're interested in. I labeled three currents, I sub 1, then I called this I sub L because that's something we want. And then this other one you could call anything you want, but I'll call it I sub C. And very quickly we can write three equations from Kirchhoff, right? So Kirchhoff's current law says that current through that resistor I sub 1 has to equal the sum of the other two currents. Then we can take a loop law, Kirchhoff's voltage law, across the outer loop. So that says that the input voltage is equal to the sum of the voltage drop across R1 and the capacitor. And so I use that as E sub O because that's a variable we're going to want going forward. And the last one is the equation about the inner loop, right? So E sub I is equal to the voltage drop across the first resistor, the second resistor, and the inductor. So it's good to take a minute and take a look at these three equations and figure out what they're telling us, and think about where we're headed, and you start getting a sense of where we want to go. So that second one is E sub I and E sub O. So there's an input-output for the E sub O, but we have to get rid of I sub 1. And the third one is I sub L and E sub I. But again, we have to get rid of I sub 1. So that takes us back to that current law. It says, well, can we get rid of I sub 1? And we can, but that introduces yet another new variable, I sub C. So that suggests a suggestion, but it doesn't quite solve our problem. But again, if you look at those three equations, you realize we never really accounted for the dynamics the capacitor introduces, right? In fact, C doesn't show up in any of those equations. Well, that should be a flag that we need to do something else, right? And so go to the elemental equation for capacitor, and you can write that next equation, which is I sub C. That current is equal to C times the derivative of the voltage across it. And so I think now we see we got enough pieces to the puzzle, we can move forward. So we take that we take that current for I sub C and substitute that back into equation 1, and we get this new kind of a recapitulation of the current law that says that I sub 1 is equal to sum of the derivative of E sub O times the capacitance plus I sub L. Now we have three equations with all the variables we need and no extraneous ones. So now it's just a question of solving and substituting. So the first thing I'm going to do is get rid of I sub 1. I sub 1 here is nicely defined in terms of E sub O and I sub L. So substitute that into equations 2 and 3 to get us two new equations. So I did both of these in parallel. So I substitute that I sub 1 into the second equation and get this first order differential equation in E sub O, E sub I, and I sub L. So we have a E sub O and its derivative, we have the input, and then this what we would call a coupling term, right? We do the same thing for equation 3, put in our new expression for I sub 1, go through the simplification, and we have a first order differential equation in I sub L with the input and this other coupling term relating back to E sub O. Interesting, this term's the coupling term is a derivative of the other variable, which is fine. We can do this just fine using the D operator. So if we go to the D operator, we have these new equations 6 and 7, which are just those first order differential equations expressed in operator form. So now we go back. We're ready to actually start answering the questions we were asked. So if we go back here to the problem statement, write the differential equation that relates the voltage across the capacitor to the applied voltage. So here is a differential equation in E sub O, and here's the coupling term, so we got to get rid of it. So it suggests clearly solve equation 7 for I sub L and then substitute that in. I sub L is this ratio here, so we've got a polynomial in D in the denominator. Substitute it into what was equation 6, and we have E sub O, here's E sub I, E sub I, E sub O, and this polynomial in the denominator that we multiply through. And now it's just simplification. Here's a multiplication of two polynomials. Here's a here are expressions with E sub I and another E sub O term that shows up here that we'll have to pull over to the other side of the equation. Doing some simplification, seeing I made some mistakes. That term, I don't know what I was thinking there. These slash marks are showing cancellations. See, this is R1 squared CD, and here's minus R1 squared CD that came over from that right hand side. We have a similar cancellation that shows up in the right hand side, and we have a differential equation that is just an E sub O. So here's a second order polynomial, a quadratic, operating on E sub O, and a first order operating E sub I. Turn it back into a differential equation, we have this nice compact form. And here's one of these cases where we have a derivative of the input. We have, we'll call this input dynamics or numerator dynamics when we get further down the road. So part B, which is find the differential equation that relates the inductor, the current through the inductor I sub L, to the applied voltage, just going in the other direction, right? Solve equation 6 for E sub O, substitute it into equation 7, and you can walk through this. Hopefully at this point it makes perfect sense. We have get rid of this polynomial in the denominator, and look, we have a product of two polynomials that was the same product we just did. I went through and redid the multiplication just to prove to myself it was fine. If you're lazy, you can just say, oh, I know they're the same, and work it out. We have slightly different things on the right hand side, but at the end we end up with a second order differential equation I sub L, and now the input is just E sub I, so it's a different input, which is what we find when we do these different input output models based on different outputs. But the differential equation, the left hand side, the coefficients of the derivatives are the same, which of course becomes the characteristic equation. So part C is, what's the characteristic equation of the two differential equations? Well, they're both this quadratic. So the last part is where it gets a little more interesting. So I said, what can you tell about the system response based on these values if you have the numerical values for the parameters? So I put those in there and find the different coefficients. So LC times R1 is this product, that's 10 to the minus fifth, and work it through. And so your quadratic, the characteristic equation, is a quadratic in D with these coefficients. Everyone by now should know the quadratic equation. I'm a big fan of MATLAB, so I just fired up MATLAB and used the roots command to find the roots very quickly, and it has two distinct real roots, minus 10,000, minus 100. So we know the characteristic equation then gives us the form of the homogeneous solution, which is the characteristic of the response of the system. So we know that it'll be two exponentials. One is minus 10,000 t, and the other one is the exponential of minus 100 times t. And what we'll see next week is that the inverse of those roots, those characteristic values, have the units of time, and we'll call them time constants. So the smaller the time constant, which is the same thing as the bigger the root, the faster the system is. So the time constants, for example, associated with the root of minus 10,000 is 10 to the minus 4, so a tenth of a millisecond. The one associated with minus 100 is 0.01, or 10 milliseconds. And so those tell us that the responses will be of those orders, of the order of 10 milliseconds, or 10 to the minus 4 seconds, a tenth of a millisecond. And which just tells you it's going to be very fast. It also tells you that the response related to that first pole, the minus 10,000 pole, will be much, much faster than the second one. And in fact, what we would find if we were to simulate this or build this circuit and look at it, we wouldn't see much evidence of that first response, because the slower response would dominate the behavior of the system, and we would see very little evidence of it unless we really blew up the oscilloscope and really stretched out that time scale. But from a practical standpoint, it's not interesting because it doesn't really contribute to the dynamics of the system very much. So that's it. That's problem 2. I know it, like I said, once I know the solution, I can walk you through a very direct route, but I sympathize with the fact that it's rarely a direct route, that you're often really moving around a lot trying to figure it out. But that's it. That's the end of problem set 1, and we're moving into a new module for next week.